Okay, so I suggest to start. So welcome to this first speaker of this Monday's talks. So now we have Rico Zacher, an expert on nonlinear PDEs that comes from the Institute of Applied Analysis in Universität in Germany. So please.
Thank you for the introduction. And I would also like to thank the organizers for the opportunity to give a talk in this very interesting seminar. So I'm going to speak about a recent project, which is joint work with my former PhD student, Frederik Weber, who is now at the University in Münster, Germany. This project deals with Li-Yau and differential Harnack inequalities for a class of non-local in space diffusion equations. So, and to begin with, let's have a look at the classical Li-Yau inequality. So here we look at the heat equation in RD, dTu minus Laplace u equal to 0. And the statement is the following. So we consider a positive solution of the heat equation, a global positive solution, U, and then the Li-Yau inequality says that minus Laplace of log U is bounded from above by the dimension over 2 times T. So this is the classical Li-Yau inequality, and you can reformulate this inequality as follows by using the equation for the logarithm of U. So if U solves the heat equation, then you can also write down an equation for the logarithm of U, which is this one, dt log of U minus the Laplacian of log of U is equal to this gradient term. So by looking at the logarithm of U, we transform the linear PDE here into a nonlinear one. And using this this identity, yeah, we can replace now this term here by the inequality, and you end up with this equivalent formulation of 1. So this is a famous result, which is due to Li and Yau, who could even show that this result extends to the case of Riemannian manifolds, provided you have non-negative curvature. And this is a famous work which was done in the 80s, and more comments on this. So 1 and 2 are sharp. You can see this by taking the heat kernel. Then you have equality. And an important consequence of 2 is this Harnack estimate given here, which is obtained by integration over a suitable path connecting these 2 points. And again, this is a sharp estimate. So this is an important consequence of this inequality 2, which is also called a differential Harnack inequality, since you get the Harnack inequality by integration. Yeah. And once you have such Harnack estimates, you can also use them to derive heat kernel bounds. So this is important in the case of manifolds. And this was actually the philosophy of Li and Yau, to first derive a differential Harnack inequality like this, then to get the Harnack estimate. And then from the Harnack estimate, you can in turn obtain heat kernel bounds. So this was the philosophy. And now let me show you a sketch of the proof, how you can show that 2 is satisfied, or 1. So how can we prove Li-Yau? So I told you already that the logarithm of U solves this evolution equation where now you have this gradient term on the right-hand side. This is a consequence of the chain rule for the Laplace operator. When you take the logarithmic function here, you get these two terms. And so when you do this transformation, you get this equation for log of u. So the goal is to derive this inequality. Okay, so how can you achieve this? Well, the idea is to derive an equation for the Laplace of v. So what are you doing is that you differentiate equation 3. You apply the Laplace operator. So let's do this. Okay, on the left, we get the Laplace of v inside this time derivative, and then we have Laplace of Laplace v. And on the right-hand side, we have to take the Laplacian of this gradient term. Now, this is a simple calculation. You get these two terms. Here we have the Hilbert-Schmidt norm of the Hessian of v to the power 2. So, and let me mention at this point that in case of a Riemannian manifold, you would have a third term involving the Ricci curvature of the manifold. Now, if the Ricci curvature is bounded from below by 0, you can just drop this term and you can proceed as we do here now, since we are only using inequalities now. Yeah. This identity here is when you apply this Laplacian to this gradient term and you have these three terms in general, it's also called Bochner's identity. Okay, now what comes next is now to use an inequality for this Hessian. And this is an example of a so-called curvature dimension inequality. Here it's a rather simple inequality. You just use Hölder's inequality and you drop all the terms which are not on the main diagonal of the Hessian. Yeah, so you can estimate this term here from below by the square of Laplace v up to some constant. And so using this inequality, you get this, let's say, parabolic inequality for the Laplacian of v. So Laplace v is a super solution of the corresponding equation. And now the idea is to use a comparison argument. So if you take this function omega of t, which is minus d over 2t, then this function solves exactly this nonlinear ODE, yeah, so which has the same term here on the right-hand side. And so this omega is a solution of this nonlinear parabolic PDE. And so formally you can say, well, a super solution is always greater than a solution, and you would get this inequality, which is the desired one. Of course, this is not a rigorous argument, but you can make it rigorous by using suitable cutoff functions. It's just to give you the idea. Yeah? So it's just, you use the equation for the logarithm of u, you derived an equation then for the Laplace of the log of u, you have some identity, and you use a so-called curvature dimension inequality, and then the comparison argument. Okay, so now let's turn to the non-local case, where the fractional heat equation is the most prominent example. So now, instead of the Laplacian, we have a fractional Laplace operator here. So here with power beta over 2, where beta is from the interval 0, 2. So there are several ways of defining the fractional Laplace operator. So one way is to use this principal value integral, where you integrate these differences here against the singular kernel. So this is one way of representing the fractional Laplace operator. And now the question is, do we have a Li-Yau inequality for equation 4 as well? And if so, how does the right-hand side depend on time? Yeah, so before we had a behavior like 1/t, and the question is this similar here, or do we get another function? Yeah, so this problem has been addressed in a recent survey by Garofalo, where this is seen as a key open problem for the fractional Laplace operator. So let me mention here that Garofalo, he's an expert who works in geometric analysis, so he's well acquainted with the notion of curvature dimension inequality, and he's in particular interested in such inequalities. But this is just a comment. So now, if you try to follow the line of arguments I've seen before for the Laplace operator, you are confronted with two major problems. First of all, you do not have a differential operator, so there is no classical chain rule. So we used the chain rule in several places. First, when deriving the equation for the logarithm of u, and then also when we applied the Laplace operator to the equation for log of u. So a certain calculus is needed here. And then the second problem is that there is a significant difference between the local and non-local case with regard to curvature dimension inequalities. So the equation which I showed you before for the Laplace operator is nothing else but the so-called CD0D condition, where C refers to curvature and D to the dimension. That's the classical curvature dimension condition. In the sense of Barkey and Emery, those of you who are familiar with Dirichlet forms and the gamma calculus, they might know these conditions. Also, they are expressed in terms of the Carré-Duchamp operator and the iterated Carré-Duchamp. But I do not want to go into details here. What I want to emphasize here, there's no such inequality in case of the fractional Laplacian. So for all positive numbers n, for all dimension parameters n, this condition is violated, in case of the fractional Laplacian. In this sense, we are saying we have the fractional Laplacian has infinite dimension. That's a big problem. So if you want to follow the path of proving Li-Yau via curvature dimension inequalities, you are in big trouble. And actually, this was quite a shock when we found this counterexample here, together with Adrian Spener and Frederick Weber. Okay, so what else can we do? Now, while reading the survey of Garofalo, we got to know another approach to Li-Yau inequalities, which works for global solutions. So let me point out here that this technique of Li and Yau with the maximum principle and the curvature dimension inequality, it can be localized. You can also look at local solutions and you prove a local Li-Yau inequality and so on. Now, for global solutions, there's also another technique which is based on a so-called reduction to heat kernel principle. So let me explain this again for the heat equation. So the key ingredient here is the following inequality, formulated here as lemma 1. So here we consider a function Pf, which is expressed in terms of such an integral, where we have a positive function f integrated against a positive kernel h. Now you can think of the heat kernel for fixed time. So, and for, so under sufficient regularity, we can prove the following or not really, it was known before, one has the following inequality. So let's look at the right-hand side. So here we have the gradient log PF at x, take the modulus, and then we square it, and then we multiply by the function. So PF is given by this integral. So now what the inequality tells us is that we can move out the integral. So we get an estimate where we have now the integral. And here we have the same structure as on the right-hand side. So we have the gradient log, and now it's the kernel h modulus squared times the kernel. Yeah? So it's the same structure as on the right-hand side. Yeah? So you can think of moving out the integral. So this looks like somehow convexity inequality, Jensen type inequality. In fact, this, to prove this is not difficult. You just use Hölder's inequality. So let me show you the proof. Okay, so let's take a partial derivative of Pf of x. Okay, here we can take the derivative inside, and so we have the derivative of the kernel. So then we square this expression, so we have this term. Now the idea is to use Hölder's inequality. So we add a factor 1 over square root of h and another factor square root of h, and we use Hölder's inequality, and we get these two integral terms. And now with the h downstairs here, and here we have just the kernel h. So here this term is nothing else but Pf of x. And so what remains to be done then is just to use this chain rule for the gradient. So the gradient of log g is the same as gradient g divided by g. So you use this identity inside the integral to rewrite this term in terms of the gradient of log of h. Of course, we sum up. Yeah. So we take the sum over all I from 1 to n, and then we use this chain rule. So we apply this here, but we also apply it on the left-hand side. So we divide by this P of f, pardon. So we divide by this, and then we use it here again, and then we find this inequality. So it's a simple estimate, but very useful. And that's the key for this reduction principle I want to show you now. Okay, so now let's take the heat kernel. And for the heat kernel, you can compute, and this is actually what I mentioned before when I said that we have equality in the Li-Yau. Yeah? So when we take the heat kernel and we differentiate with respect to x, then we get exactly this d over 2t. Now, let's consider a positive solution u of the heat equation. Now, we have seen already the equation for the logarithm of u. So this is now a little bit, I mean, it's written in a little bit different way. So here I do not have the dt log u, but I wrote dt log u as dtu divided by u, and I multiplied by u to get this form. Because here we have this structure we have seen before in the inequality. Yeah? So it's this structure with the gradient log modulus 2 power 2 times the function. It's the same structure here. So this is true for any positive solution. So in particular, it also holds for the heat kernel. So we have dTh, and now here we use this identity. We plug it in, we get plus h times phi, and on the right hand side we have this term now with u equal to h. Okay, to keep this in mind, that's the identity for the heat kernel. Now, it is known that any positive solution, strong solution of the heat equation, can be expressed as an integral where you convolve with the heat kernel. that's a Witter type theorem, important result. So this is what we need now. So we have this representation for u. And now let's look at dtu plus phi of t times u. Okay, so now we insert this integral representation, then we take the derivative. So this means here we have to take the derivative of h. And then for the second term, we just have phi of t times the kernel and the initial value naught. Okay, now this term here in brackets is exactly the one we have here in this identity on the left-hand side for the kernel. So now we use this identity for the heat kernel. And we have this gradient term now. Okay, and then comes the step where we use lemma 1. So here we have this integral, we have this nonlinear structure, say, on h times the initial value. And so the lemma tells us we can now move the integral inside. We get an estimate from below by the gradient log u modulo square times u. That's the lemma from before. And now using again the equation for the logarithm of u, we can rewrite this in this form. And then the dtu cancels out. We can divide by u and we end up at the desired inequality. Yeah. So that's a very nice argument, I would say. And actually what we need here is only this inequality, not the equality. It's just this inequality. So to summarize, we see that roughly speaking, Li-Yau for the heat kernel, which is this inequality here, implies Li-Yau for any positive solution. So that's the story here. And the question is, can we do the same for the fractional heat equation? Is there a similar argument? Now, again, there are several problems. So the first one is, what is the equation for the logarithm of u, right? So suppose u is a positive solution of the fractional heat equation. Then we can write down an equation for the log of u. And this takes this form here. So here we have the parabolic operator on the left-hand side. And on the right-hand side, instead of the gradient term, we have this operator psi upsilon, or palm, with this function upsilon or palm tree, which is the exponential of z minus 1 minus z. So this operator here is given via this integral, where we look at this upsilon of this difference, and then again integrate it against the kernel associated with the fractional Laplace operator. So this identity was already observed in a previous work by Dominique Dier, Moritz Kassmann, and myself, where we actually studied Li-Yau type inequalities on graphs. So this is already good news. So we have some equation for the logarithm of u, and you can rewrite it again as before just by rewriting this as dtu divided by u. You multiply by u, so this is then the equation we would like to work with. But before we move on, let me show you the idea behind this identity. In fact, it follows from a simple algebraic rule for differences. So let's have a look first at the classical rule, which is written on the bottom. So we have the Laplacian of log u is nothing else but Laplacian of u divided by u minus this gradient term. Okay, so now let's try to find something similar for the non-local operator. So now, in the non-local case, we have to look at differences. Yeah, so we look at the difference log u of y minus log u of x. Yeah? I mean, in the end, we have to multiply with the kernel and then to integrate, and we have the operator. So it's basically a rule for differences. So let's rewrite this. Now we would like to have something like this one here. So we write down the corresponding term, which is now the difference of the u's divided by u. Okay, and then we have to correct everything. And the correction term looks like this. Yeah, so we have this one. And now the nice thing is that we can rewrite this in terms of this palm tree function of log of u of y minus log of u of x. Yeah, so this is just simple algebra, which is behind this chain rule for the non-local operator. So this is now the corresponding identity. Okay, so maybe I should mention here that when you look at the expansion of this function epsilon of z, so the first term in the Taylor expansion will be z squared over 2. If you just take this square term instead of the epsilon function, you will have exactly what is called the carré de champ operator of log of u, yeah? Which is an object that is important in this gamma calculus, which appears in the curvature dimension inequalities. And also in the classical case, when you have the Laplace operator, this gradient log u term is nothing else but the carré de champ operator of log u. So here the point is, we see that we do not have a carré de champ operator anymore. It's a different object. Yeah? It's not just a square, but we have this function here. So in some sense, the message is the square function from the local case is somehow replaced by this function here. Okay, so this is what is behind this chain rule identity. Yeah? Okay, so now I would like to remind you of the key inequality from the local case, which was this one here, where PF was given in terms of such an integral. Yeah. So it turns out that we can obtain a similar inequality now with this operator here we have on the right-hand side. And this is now a key ingredient in our approach. So under the same assumptions on the involved functions, we can show that this psi epsilon log PF times PF of x term can be estimated from above by the corresponding one, where we move out the integral, yeah, and where we have the same structure now on the heat kernel. Now, that's a nice inequality which paves the way to extend this reduction to heat kernel principle. That's the key ingredient. It takes some calculations, but at the core of the proof is a Jensen's, an application of Jensen's inequality, where you use the convexity of this function here. That's the key part of the proof where you get the inequality. Okay, so this is good news. We have now found the right replacement for this inequality, and we can now move on with our program. So, as I told you, it's crucial here that we have a representation of the solution in terms of the heat kernel. Now, fortunately, there's also a Ritter type theorem known in case of the fractional heat equation. This is a result which was obtained by Barrios, Peral, Soria, and Valdinocci in 2014. So we can use this result. Any positive strong solution of the fractional heat equation can be expressed in terms of a convolution integral, where now we have the fractional heat kernel, G beta. Okay, so now we have all the ingredients together, so we can apply lemma 2 now with this fractional heat kernel, and we can argue as before to obtain the following implication. So if the fractional heat kernel satisfies this Li-Yau inequality, if this is true, then we get automatically also this inequality for the function u itself. Yeah, so this is this reduction principle. And so everything boils down to the question now, for which functions phi do we have such an inequality? This is now a question about properties of the fractional heat kernel. Now, unfortunately, there is no nice analytic expression for the fractional heat kernel, except for the case where beta is equal to 1. Nevertheless, one knows quite a lot about fractional heat kernels. One knows bounds from below and from above. One knows that it has a self-similar structure. And so one can try to prove something like this for suitable phi. And in fact, you can show that this expression here is bounded from above by a constant divided by t. So we have the same behavior as in the local case. And this constant CLY, which depends on beta and d, is given in this rather implicit form. But nevertheless, we have some expression for this constant, where here this function phi sub beta is given as the fractional heat kernel at time equals 1. So that's just the heat kernel for time equal 1. And part of the statement is that this is a finite quantity. Yeah. So in case where beta is equal to 1, you can calculate this quantity. Actually, in this case, you can see that the supremum is assumed at y equal to 0, and then you can calculate this constant, and you find this expression here in terms of the beta function. So, yeah, as I told you, the fractional heat kernel, it has a self-similar structure, so it can be written in this form, where we have this function phi beta of this similarity variable x over t to the 1 over beta, and then with this temporal prefactor. So this constant is the smallest constant among all constants for which we have this inequality. This is also part of the statement. Okay, so let me show you the argument for this. Okay, so let's look at this expression here. So here I use a slightly different form of the fractional Laplacian, where I use the representation with where we look at both sides. So we have x plus h, x minus h, and then there is this additional 2 downstairs. So let's use this this expression. So we have logs here, so we can rewrite this in this form. We have a log of this quotient, and we can use the self-similar structure of the heat kernel and perform a scaling, setting y equal to x to t to the minus 1 over beta to get this equation here. So we see that this integral here can be reformulated as 1 over t times this integral now, where we have this phi phi sub beta at y. It's a similarity variable. Now, so this is the term now we have to bound from above. We have to show that this term is bounded from above for y from Rd. So the rest is just the self-similar structure and scale. Okay, so what about this quantity? Now we decompose the integral. So here we cut away the singularity. So we look at Rd without this unit ball, and then this is the second part. Now for this first integral, we just need the bounds for the heat kernel given in this form. So we have upper and lower estimates of the fractional heat kernel in this form, and this can be used to estimate this quotient term. And since we are away from the singularity, yeah, there's no problem then with the integral. Converges thanks to this kernel here. The second term is more involved. Now we have to deal with the singularity. So here we use this inequality for the logarithm to get rid of the logarithm, and we have just r minus 1. And then you employ Taylor's theorem together with suitable bounds for the gradient and for the Hessian of this function phi beta, which are known in the literature. And here you only need the bounds for large values. Yeah. So actually you can always restrict the investigation here to y with modulus y bigger than some positive number. So for small y, you have a bound just by continuity. Yeah, and so you can restrict everything to such bounds, and yeah, and that's it actually. Yeah, so you just have to put things together and to use this estimate, and then you find the desired inequality. So let me summarize. Now we have all the pieces together. So for any beta in 0, 2, and for any positive strong solution of the fractional heat equation, this Li-Yau type inequality is satisfied, where we have this constancy before. So far, so good. Now, now let me see. Yeah, let me just make some comments. So this is a result for the fractional heat equation. But it turns out that you can generalize this result to a much larger class. Yeah? So in here I want to remind you of the nice talk given by Vasily, who considered a rather general class of non-local operators, where you have an integral and you integrate differences against a certain measure. And this is actually the key feature you need to prove such a reduction principle. So here we try to generalize it. So MD is the metric space, and then this is B of M is the Borel sigma algebra, and M, and we consider an operator in this form. It's a rather general setting, and we also include the singular case just by defining the integral then in this way, where we cut off small balls. So what is important here is the structure, and you can do the same calculations. Yeah. So the message here is really everything is based on certain rules for differences. This is an important principle, I think, in non-local equations. In particular, when you are looking for pointwise estimates. Yeah. So an important example we have also in mind is the generator of a continuous Markov chain on a discrete space. So which has this form. So here you integrate over all states of your space M, and you have the kernel kxy, which describes the transition rates, and you integrate against this this difference term. Now, so it's the same structure, and so you can also prove the reduction to heat kernel principle. Yeah, you can define the psi upsilon as before. We have the same chain rule for the operator L, and you also have a generalization of what I've showed you before, the key lemma, where you move out the integral, everything can be generalized, and so in the end we get a more general result. Yeah. So now we have to assume that our solution U is given in terms of the heat kernel. So for the heat equation, for the fractional heat equation, this was somehow provided or ensured by the Witter theorem. Here we have, in general, we don't know. We have to assume it. Yeah, so we have a positive solution of this non-local diffusion equation, and then assuming also some technical assumptions. And this estimate for the heat kernel, which is the Li-Yau inequality for the heat kernel, we get the corresponding Li-Yau inequality for U. Yeah. Okay, and let me illustrate this with a discrete example. So here we look at the unweighted complete graph Kn. So we are in the Markov chain setting. So this is our state space, points 1, 2, and so forth to n. And then we look at this operator L here, where k is equal to 1 whenever x is not equal to y. And in this case, I mean, of the complete graph, you can calculate the heat kernel. It has this representation, and then you can look at minus L of log of P. You can also calculate everything, and you see that the maximum is assumed at y equal to x. And so you find this Li-Yau inequality for positive solutions on the complete graph. Now, this is just as an illustration that we can go much further with this reduction principle. It's a rather general result for non-local operators. Okay, so far so good. So we have Li-Yau inequality, but now the big question is, does this Li-Yau inequality also imply a Harnack inequality? Yeah? So I mentioned at the beginning, the philosophy of Li-Yau was first prove differential Harnack estimates or Li-Yau inequalities derived from this, the Harnack inequality. This was the most important application, and then heat kernel bounds. Yeah, so here the story is a bit different. So we use heat kernel bounds to get the Li-Yau inequality, but what we should also prove somehow is now the Harnack inequality. So is this Li-Yau inequality strong enough to obtain a Harnack inequality? This is now a fundamental question, of course. Okay. So let me remind you that in order to prove the Harnack inequality, one uses this form where we have the time derivative of log u. Now, this was the differential Harnack inequality. Yeah. And now, in contrast to the classical case where we had this gradient log u term, we have this non-local operator involving this function upsilon. Yeah. So, and So this is a highly non-trivial problem. Yeah, in the classical case, you have this gradient term. You can just look at trajectories connecting the 2 points, and you have the gradient squared somehow to control everything. So this is no longer possible now here in this non-local setting. So, but there were already some positive results in the discrete case. So when we look at diffusion on graphs, so there it was shown that indeed you can use such inequalities to prove Harnack type estimates. So this is a good structure. And in this connection here, I would also like to mention these 2 papers. The first one, let me call it by the Harvard School, where Li-Yau himself is involved. This was the first paper on Li-Yau inequality on graphs. And then there's another important contribution by Florentin Münch, who developed further the calculus from the first paper. But let me mention that in this, let's say, Harvard paper, people were not using the logarithm of u, but the square root, since they somehow could not cope with this lack of chain rule. And then it worked as well, but the results were not so strong. But anyway, this was just a remark. So in the discrete case, things go well with this inequality. But in the case of the fractional Laplacian, things are much more involved. So as I told you, you cannot argue just by integration along path, since you do not have a control of the gradient, so you have to use somehow appropriate jumps. So, but it turns out that in fact this inequality here is strong enough to imply a Harnack inequality. And this is the one we could obtain from this Li-Yau inequality. Yeah. So here we have a bound for ut1 x1 in terms of ut2 x2. Then there's this similar factor as on slide 1, now with this Li-Yau constant in the exponent, and then there is some exponential term. So let me mention here that the point here is not the Harnack inequality as such, but the point is that we are able to obtain it from this inequality, from the Li-Yau. Yeah? So there's already literature on parabolic Harnack inequality for space fractional heat equations. So let me mention here Bess and Levin, and also Chen, Kumagai, who were able to prove Harnack estimates by means of probabilistic methods. And later on, Chang, Lara, and Davila, they were able to prove or to give a purely analytic proof, even in the rough setting where you have an operator in divergence form with rough coefficients. But you can also use the heat kernel representation. If you have a global solution, you can work directly with the heat kernel and suitable estimates to prove Harnack estimates. And if you use the heat kernel, you see actually you do not need a time gap between T1 and T2, like in the classical parabolic Harnack inequality. So this is that's a significant difference to the classical case. And here in this result, we are not able to cover this case. So in this case, it's not a sharp and optimal result, but at least it is a Harnack inequality, and that was the main point for us. Yeah. So, okay. So let me show you some ideas of the proof. So in order to prove the Harnack inequality, we have to estimate this term here, the log of u at t1 x1 divided by u at t2 x2. If we have a bound for this term, yeah, then we can just take the exponential function and we get u at t1 x1 is less than or equal to u at t2 x2 times the exponential function of this constant. Yeah? So this is the goal, to find a suitable bound for this expression. Now, how can we achieve this? So we write this expression here as a sum of three terms. In the first term, we just replace the t2, so we have t1 x1, and then we take u at s x1. Then in the second term, we consider u at s x1 and u at s x2. This is this one here. And in the third term, we have u at s x2 and u at t2 x2. So, and the first and the third term can be rewritten using the fundamental theorem of calculus, in terms of the time derivative of the logarithm of u. Okay, and now you can estimate, thanks to the differential Harnack inequality, you can estimate now this minus dt log u from above. Yeah, so, and this results in this inequality here. So we have the two psi upsilon terms we get from the differential Harnack inequality. So this term is still the same. I just copied it. And then we have two terms resulting from this function here, and we bring them together to integrate from t1 to t2. So here we use the differential Harnack inequality. So, and this identity is true for any s in this interval, t1, t2. Now, so the problem is, let me go back. So the problem now is this is something fixed, right? And here we have this term with this time s, which we have to control using these two good terms. So this epsilon function is a non-negative function. So these terms here are negative terms. And the goal is now to use them to control this one. So how can this be done? So let me introduce this function f. So now s is replaced by t now. So we have v at t x1 minus v t x2. And then we subtract the two non-local terms. Now the idea is to choose s, the time s, such that you minimize the function. Yeah. So you choose s such that f of s minimizes the function over this interval t1, t2, and so you can estimate this minimum then by the integral. And here we have to incorporate a suitable positive weight function, eta. Yeah? And we can then estimate this term in this way. And now let me maybe go a step back to explain the difficulty here in comparison to the local case, to the discrete case, pardon. So in the discrete case, yeah, you have just u at s x1, u at s x2, and suppose the 2 points are neighbors. Yeah. When you have these non-local terms, here you have an x1, so you have log u, and then you take all the differences. You have log u at x2 minus x1, okay, but you also, from this term, you would have something, the epsilon function applied to a log u at tx1 and minus log u tx2. Yeah, and so you have the same difference as you have here, and then you can control this term just by using the second term here. So this is, you just pick one point, the right point, the right neighbor, and you drop the rest and you are done. And this is no longer possible in the continuous setting. You cannot just pick a point because you have an integral, and there's no mass anymore. So that's the problem. And this is why you have to use a suitable weight function, and you have to use the singularity of the kernel. And so to go further here, so we have this expression. So we can rewrite this integral as follows. So here we had vtx1, vtx2. Let me subtract and add vt of y. And then we introduce these averages over a suitable set qt. And so using these averages, we can rewrite this integral in this form, where as to the non-local terms, we use Fubini's theorem to reformulate this. And then, let me show you how we choose the set qt. It's a ball with a radius that depends on time t in a suitable sense. So it's a ball around x1, and the radius is given here by this formula. And then the weight function is of this type here. So we have it vanishes at t1 and it vanishes at t2, and you have a suitable power alpha, which you have to choose big enough. And then to finish just this sketch of the proof, you have to use both non-local terms. And the problem actually is that this function upsilon is not symmetric like the square function. So for the square function, you have a quadratic behavior for positive and negative z. So here things are different. For positive z, you have an exponential growth. For negative z, you have only linear growth. And this makes it difficult. So for negative arguments, you can only use somehow something like this. But for positive arguments, you can use a quadratic estimate. And so you have to combine things in a clever way to get the estimate. It's a bit tricky, but it can be done. And it is really significantly more difficult than in the discrete case, where you just pick an appropriate point out of your non-local operator. Okay, so my time is up. So I will stop here, and thank you for your attention.
Thank you so much for this clear and interesting talk. So now if you raise your hand, we can proceed to questions or comments. So, yes.
Hi.
Hi.
Anya Wagner, joining in from the Moller Institute. There's a couple of us here listening to your lovely seminar. Thank you. So I have a question about the Li-Yau constant. So you said it's a sharp constant in this alpha stable case. Does it by any chance recover the constant for the Laplace operator once you push alpha to 2?
That's a good question. We don't know, actually. It's that's one of the, I mean, there are several open questions, but this is certainly one. So we have this constant here. Is it here?
9, yes.
Yeah. So yeah, it would be nice to see how this constant behaves when beta goes to 2. Yeah, this is an interesting way. Another thing is, of course, do we or can we show that the supremum is assumed at the point y equals to 0, which is the case for beta equal to 1. And somehow one would conjecture that this should be true. Yeah, once you know this, then you have a chance maybe to calculate this constant and what to do some asymptotic considerations. Yeah.
Okay, thank you.
Yeah.
Other questions?
Vasily.
Yes.
Yes, Rico, so very nice talk, of course, thank you. Very natural question, of course, arises. You make fractional special. What about fractional temporal derivative?
Okay, that's a different story. So actually, when I started to deal, I mean, to study non-local PDEs, I actually started with fractional in time problems, and I always try to prove a Harnack inequality for this for the time fractional diffusion equation, and it turns out that if the dimension is at least 2, then the classical parabolic Harnack inequality fails to be true. So you can give a counterexample using the properties of the corresponding heat kernel of the fundamental solution. Yeah, this is in dimension 1, I still believe in a Harnack inequality, and in fact for global solutions it is also known, but in higher dimensions it is not. It's not true. Yeah, so, and this is why I think it's. I mean, it doesn't make so much sense to look at Li-Yau inequalities, because one of the most important consequences should be a Harnack estimate. Of course, one can ask, maybe there's another formulation which somehow is able to capture this, but yeah. So, but this is actually what I tried first, and then I somehow at some point I found these papers on graphs, and then we, together with Moritz Kassmann, we thought, well, maybe it's a good idea to look at the fractional Laplace operator, and yeah.
Okay, thank you.
Okay. Any other question or comment?
I mean, I can make another comment concerning the approach via curvature dimension inequalities. Yeah, so I told you at the beginning, there are these counterexamples. There's no CD inequality like for the Laplace operator, but of course, it would be nice to have somehow a proof of the Li-Yau, which relies on suitable curvature dimension inequalities, let's say for the fractional Laplace operator. Yeah? Because this would be really in the philosophy of Li and Yau. So you first derive the Li-Yau inequality. Now we know how it should look like, then you can derive the Harnack, and then you can prove heat kernel bounds. And this should be also possible then on manifolds, right? So, and concerning this curvature dimension inequalities, that's really a very interesting open question. And what we know is that there is a positive result in the discrete case when you have the fractional discrete Laplace operator, let's say on the integers. Then we are able to prove a curvature dimension inequality, and from that we can also derive Li-Yau and Harnack. In the discrete case, this is possible, and it is quite interesting because the kernel of the operator somehow determines the form of the curvature dimension inequality. Yeah. So maybe but this no longer works for the continuous case. So I told you about this curvature dimension inequality. So if you have a Markov generator L of a Markov semi-group, yeah, you define this Carré-Duchamp operator gamma of u and v in this way, and then you iterate this. You define gamma 2 u and v. Now you apply L at gamma of u and v and so forth. And so if you take the Laplace operator in RD, this gamma u of v would be just gradient u times gradient v, and the gamma 2 is more or less when you take u and v the same, the Hessian matrix of u, the Hilbert-Schmidt norm of the Hessian matrix power 2. And so the curvature dimension inequality I mentioned in the sense of Barclay and Emery is an inequality of this form, where you have an estimate of gamma 2 from below by the square root, not by the square of LV plus a curvature term. And here you have the gamma. So what concerns Harnack, we do not need this curvature term. We just use the square in this argument I showed you. But such a square is not possible to get in the non-local case in general. So for the fractional discrete Laplacian on the integers, we are able to get an estimate where we have to replace this term by another one, and here you have a certain power. But a higher exponent. You cannot use 2. But it's a very interesting project, and this is where we are working on now. Okay, so thank you.
Okay, thank you. So we are going to start back at 8 UK